this part is the definition of beta distribution. This part here, gamma A plus B over gamma A multiplies gamma B is a constant. Because now in this equation, in this function, we are talking about we are interested in mu. So all the terms do not have mu is a constant. So we can drop it. And then do some rearrangement. So if we introduce a prior probability of mu with the beta distribution, we get that the posterior of mu given the data set is like this. Similarly, we maximize it with respect to mu. We will get so this is under the MAP estimation, the estimation of mu. Compare with the estimation of mu in MLE, we can say that on the numerator and denominator, we add some values. Intuitively, it is something like, remember that in that part we call N1 the counts. And here, alpha A and B are not from the data, but from our prior knowledge. It's something like the pseudo counts. So suppose take in the extreme case, we observe no data, which means that both N1 and capital N are 0. We still get a reasonable quantity, which is alpha minus 1 over alpha plus B minus 2. So you can regard this as something like the counts we talk about in the data. We see that the estimation of MLE is purely from data, and the estimation under MAP is a combination of data and the knowledge. So in this equation here, N1 and N are the data, because you count these two quantities from the data samples. And the A and B here are the knowledge. Even if you have no data, if you do some assumptions, say A equals to 1 and B equals to 1, you can still get an estimation of mu. So here part reflect how your knowledge about this is parameter. Okay.
Alpha and beta are just your priors? Are they like parameters for your priors?
Sorry, A and B. A and B are the parameters of this beta distribution. Yeah. So in this distribution, the parameter, the random variable now is mu, and the parameters are A and B. Remember that when you are study a distribution, we should distinguish these two kind of things. So in the Bernoulli distribution, mu is the parameter of that distribution, but here it is a random variable. You mean here? No. Because you have some value of A and B, right?
Yeah, so if they're both 1, you just gave an example, right? If you start with alpha being 1, beta being 1, then in all examples you're going to have 1 plus 1 minus 2, right?
Let's see. Suppose I have no data, which means that n1 equals to 0 and n equals to 0. But I have some prior knowledge that A equals to 5 and B equals to 6.
No, but what I'm saying, like, I thought you were saying that when alpha is equal to 1 and beta is equal to 1.
Oh, sorry. I'm just trying to give an example. You can think alpha A equals to 1, A equals to 2, and B equals to 3, something like that. Yeah.
If they're both 1,
Yes.
they're uniform.
Right. Yeah. So to wrap up here, in MAP estimation, the estimation comes from both from the data and the knowledge. And the data is exhibited here, and the knowledge is described here. Basically, A and B are playing the same role and N and 1. But they are not from data, so they are called pseudocounts. That's our understanding of A and B in this beta distribution. Any questions here?
Can you repeat that? So A is like N1 and B is like the big N?
Or
Or are they both N1?
no, it's like A plus B like. Yeah, right. Yeah. Because A is on the because A is here, defined over the shoulder of the mu, and mu is Dirichlet distribution is nothing but a generalization of the beta distribution. So when you when mu is not a, so in this case mu is not a scalar anymore. It is a vector. Remember that in multinomial distribution, we have a parameter mu vector. Each of the component means how likely the random variable will take the outcome. So this mu vector is the parameter of multinomial. If you want to put a prior over this mu vector, we should use Dirichlet distribution. Basically, the same thing as the beta distribution for Bernoulli distribution. And similarly, also, the parameter in the random variable in this distribution is mu, and the parameter is alpha. Alpha is also a vector. The length of alpha is the same as mu. And each of the component in this alpha vector is also something like pseudocounts, as we discussed previously. Any questions so far?
Just make it clear that the prior is not informative if it's uniform distributed.
Right.
That's the case when A and B are equal to 1.
Right.
Yeah, but if they're equal to 1, they're not informative because they're uniform distributed.
Right.
So in that case, that is simply MLE.
So far, we talk about the distributions over, I should say, for the continuous variables, we are going to use Gaussian distribution to model it. Its probability density function is defined as follows. Very familiar with, I guess everybody with. It has two parameters. One is mu and another is sigma square. As you know, mu is the mean of this distribution, is the expectation of this distribution, and the sigma square is the variance of this distribution. For the multivariate case, which means that the random variable is not a scalar anymore, it is a vector. We use this multivariate Gaussian distribution to model it. It has two parameters. The first one is mu, which is a vector of the same length as x, which is the expectation. And another parameter is a sigma, which is covariance of this covariance of the random variable x. By the way, covariance is defined as, because x is a vector here, it has k components. Let's say x1, x2. This is the definition of the covariance matrix. Each component, each entry of this matrix is a covariance between the COY, the IJ's entry of this covariance matrix is the covariance of xi and xj. The covariance between the i's component and the j's component of this random vector. We are done with these 5 distributions. For each of them, I think we need to remember 2 things. The first one is, what is the characteristic of the random variable it is going to model? It is discrete or continuous. If it is discrete, it has 2 outcomes or multiple outcomes. Another thing is, for each of the distribution, you should remember the meaning of its parameters. For example, in the beta distribution, we have A and B, and we said that A and B are pseudo-counts. And also the relationships between them. Beta is a conjugate pair of Bernoulli, and Dirichlet is conjugated to multinomial. So any questions here? The next topic we are going to discuss is there a general form that then can unify these 5 distributions? This comes to the exponential family distribution. Exponential family distribution is a general form which has the form of this form: Px equals to xx, xx, g eta, exp, eta transpose mu x. And the eta here is called the natural parameters of this distribution. And mu x is called sufficient statistics. As we said, all distributions we discussed so far is special cases of exponential family. Let's take an example to show that Bernoulli distribution is a special case of the exponential family. Remember that the probability mass function of Bernoulli distribution is Px equals to mu x 1 minus mu 1 minus x. We put a exp here and do the log. It doesn't change anything, right? We first do the log and then do the exp. Expand this term inside, we get x ln mu plus 1 minus x 1 minus mu. Rearrange all terms here and distill mu out. We get ln mu 1 minus mu x. Sorry, there should be a log here. Now we take this term here outside of the exponential. We get 1 minus mu let's introduce another variable eta equals to this quantity here, log mu over 1 minus mu. And then mu will becomes 1 over 1 plus e minus eta. Now we plug in the mu equals to this quantity here into the original, and we get so by doing some simple arrangement, we get the original mass function, a new form of the original mass function parameterized by eta. If you compare this form with the general exponential family form, which is Px equals to hx g eta, let's define hx as 1, g eta equals to 1 minus by following these 4 definitions here, we show that these 2 equations are the same, right? That is to say, we can write the mass function of Bernoulli distribution into the canonical form of exponential family distribution. So that this says that Bernoulli distribution is a special case of the exponential family. And you can do the similar things for all other distributions. The next question is why we care about this general form. Is there any nice properties with respect to this exponential family distribution? The answer is yes. And the most important one is called moment generating property, which is very elegant. You can see from these two equations, if you want to estimate the expectation of sufficient statistics, you just take the derivative with respect to the negative log and the g-it. G-it, remember that in that form, it is a function with respect to the natural parameters. If you want to estimate the variance of the sufficient statistics, just take the second derivative with respect to this function. And this property holds for all 5 distributions we talk about. And this gives you a very convenient way to estimate these two important quantities in a really fast way and elegant way. By the way, why UX is called sufficient statistics? It is also from these two equations. Suppose you want to estimate eta. You can see that all you need to know is UX, which means that UX is sufficient to get you a value of eta. So this is why it is called sufficient statistics. And as I said before, in graphical models, all we care about is the expectation with respect to this thing. So if you come to that part, you will need to compute this value a lot. And this equation will give you a very convenient way to do this. So the third part, let's talk about the conjugate prior. By definition, when we are talking about the posterior of the parameter, in this equation, theta is the parameter we are interested in and we want to estimate, and d is the data. So under the MAP estimation, we want to compute p theta given d. And according to Bayes' rule, it can be written into that form. So the definition of conjugate prior is if the prior distribution p theta and the posterior distribution p theta given d are from the same family, namely they are both from the beta distribution or both from a Dirichlet distribution or Gaussian. If this condition is satisfied, p theta is called a conjugate prior. To make the prior distribution and the posterior distribution from the same family, it strongly depends on what is the distribution over the data, namely this part. So if the data is multinomial. And the P set here is Dirichlet. We will get P set given D is also Dirichlet. This is one case. Another case is if the distribution over data is Bernoulli, and P theta is beta, we will get P, the posterior of theta is beta distribution. And the third case is here, in Gaussian distribution, we have two parameters, mu and sigma square. Here we are talking about the expectation of Gaussian. So if you use Gaussian distribution to model the data, and the prior distribution over the mean is also a Gaussian, then the posterior P mu given the data is also a Gaussian. Conjugate prior, as far as I know, mostly we are dealing with these three cases. Sometimes, if the Gaussian distribution, its covariance is a matrix, you can use. There is also another case of conjugate prior, but generally we don't deal with that. You can see that in the definition of conjugate pair, usually are involving two distributions. We will see these two distributions are conjugated to each other. So Dirichlet is conjugated to multinomial, beta is conjugated to Bernoulli, and Gaussian is conjugated to Gaussian. Before I show you, okay.
So what's the motivation? You spent a lot of time talking about conjugate priors. But is
Yeah.
the motivation behind it, like with online algorithms or something, when you're incrementally adding data, you want the posterior distribution to be parameterized the same thing as the prior?
That is because I think the most important reason is that if you use a conjugate pair, it will make your computation, inference, and learning much easier. For theta, you can use a Gaussian distribution, but it will make the computation really hard. Before I show you an example, do we have any questions here?
What is this data called? What does it represent?
Theta is the parameter and x is the data. Yeah. Okay. The first one? Okay. Let's take a proof. It's very simple. Because Px is a distribution, it must satisfy that its integration is 1. Okay. Okay. For conjugate pair, let's solve our example here. We have a data set D, which contains n examples. And each example is drawn from a multinomial distribution, parameterized by mu.